So here we're going to look at the effect of alternating current on a resistor in a circuit. So the supply voltage is alternating current, AC. The resistor is the component, our load, and a current will flow around this circuit. Before I move on to what the waveforms are going to look like, I just want to remind you about the sine wave. So from here to here is one complete cycle, and that takes place over 360 degrees. I want to mark on 90-degree intervals on this sheet. It's not crucial in this particular case, but in the following examples that we're going to go through, it is critical. So this is 0. The waveform rises after 90 degrees to a maximum, so that's 90. The waveform falls down to 0, and that is going to occur at 180 degrees. The waveform continues to a negative maximum, and that is at 270 degrees. And it finishes on one cycle at 360 degrees, so that's there. Okay, so let's run through some of the basics. This is a resistor. We have resistance, voltage and current, and Ohm's law applies. At each instant that this voltage increases, the current will increase to correspond with it. So the current waveform will look something like this. Okay, so the red is the current and the blue is the voltage. So what's happening in this circuit when we apply AC to a resistor? The current and the voltage rise and fall together. They rise and fall at the same time. The phrase we have for this is in phase. That is important. So the current and voltage rise and fall in phase. We don't always draw these waveforms. Sometimes we do, but we don't always do that. And there is a simple way of representing them. In electrical work, we can represent a voltage or a current by an arrow, and we call the arrow a phasor. So in this case, we have voltage. So let me represent the voltage. There's our voltage. And we also have the current. Now they rise and fall at the same time. So the current literally goes over the top. If I did that literally over the top, you'd struggle to see it. So there is the current. And if I'm going to be pedantic, then literally at this point in time, I've drawn two arrows on my page to make them into phasors, which represent the values that we're talking about. I need to mark on that these rotate anti-clockwise. So they rotate in an anti-clockwise motion about that point there. And to tell me that this rotation is to do with the frequency of the supply, I write by the arrow the Greek letter omega. We've met omega before. There's capital omega, which we use for ohms, and lowercase omega is like a curly W. Okay, so I'll give links to a video clip that you can watch this later on. So these phasors represent these voltages, and these become increasingly important over the next few pages. So we've spoken about Ohm's law applying, and it does literally apply with V, I and R. So in this circuit, V equals I times R, no change there. I equals V over R. And finally, R equals V over I. So even though we've changed from a DC supply to an AC supply, Ohm's law will still work. Let's do an example. Okay, so here's a simple question. A 75 ohm resistive load is connected to a 230 volt AC supply. What is the current flowing? Well, just because we've changed to AC, there's nothing special happening, and Ohm's law applies. I equals V over R. Put your numbers in. 230 divided by 75, and that comes to 3.07 from memory.